Hello guys, today we're going to learn how to create AXI master through Vivado HLS. Up to now we learned how to create IP cores which use the AXI-like interface, the AXI stream, and now we're going to learn how to do the AXI master. The idea of this tutorial, for instance, is to show how to create an IP who could write directly to the memory, like you can imagine like a DMA or something like this. Okay guys, hope you guys enjoyed. Now we are going to go to the lab and let's go. Let's learn a little bit about the AXI master interface. Okay, to create the pragma needed to instantiate an AXI master interface is this: pragma HLS interface and AXI, the depth. Actually, here you configure the burst size, the port name, and an offset. This offset is actually the address that a specific destination, for instance the NIC, has inside the interconnection. Okay? Stepping back a little bit, up to now we studied the AXI for light, the AXI for stream, and now the AXI for full. The AXI for light, as we saw in previous videos, is good for parameters or stuff that are not too big. I mean, it's not a good idea to transfer a whole image using this interface. The AXI for stream, in the other hand, is a very simplified interface protocol, but it's really useful, for instance, if you want to transfer videos and large stream of data. Okay? The AXI for full, in the other hand, is very specific if you want to also transfer data fast, but in a memory mapped fashion. For instance, imagine that you create here an AXI master block that is going to work as a memset. It's just going to initialize a large amount of memory, okay? And you want, for instance, that this guy here is initialized some addresses in the DDR, okay? So we're going to use an AXI master that is going to send some data with some address, okay? By the way, specified here, okay? And this guy, the idea is that this guy works like a DMA, like really a coprocessor. He's going to work directly without the active processing of your microprocessor, in this case microblaze. Okay? We're going to create on the lab this guy who is going to be an accelerated memset, in sort of speaking, and he's going to have an AXI-like port to set up some parameters like the value that you want to memset, the address, and stuff like that. Okay? And after you send the command start, it's going to initialize the DDR with some values. Okay? Now I'm going to switch to the lab, and we'll be more clear what we want to do. And hope you guys enjoy it. And let's go.
Will be a kind of memset. It's just an IP core that we're going to use to put some values in memory. Okay, so let's go. Lab 8 HLS AXI master. Okay. Set name. Here, as we are going to use an RTX board, we're going to actually set here for the RTX 7 family. Okay, in our case is the 50. Let me check if I found. Actually, you don't need to care about too much about the. I mean, if you set the family, it's more than enough. Okay. So now let's create our core. Okay. Let's actually make it return something. Okay. So set mem. Let's say that you're going to have a specific value. Okay. An address. Okay. Actually, let's call this, yes, let's call this address, no problem. okay, and also a size. Okay, guys. Actually, let's also create a header, because we're going to write as well the test benches, and this is going to be helpful. Okay, actually I already calculate the maximum possible value. Okay, just one point, the AXI 4, okay, master, the burst length is maximum 256 bytes. Okay, this is actually important to remember, because this will limit our burst. Okay, what else we could create? Okay, actually this will be a pointer. I forgot. Okay, and well, let's now work on our directives. So value, let's say that we want this to be a parameter in AXI light. Let's call this okay, size as well. And actually here we for the address we're going to interface as well. Actually we're going to see AXI, okay, for AXI master, okay, and the offset, actually there are two options. If we choose offset direct, a port will be added to your core, where we can just put a constant there to actually say from which address you start to write. In our case, we're going to put slave, and the slave will create an AXI light port, okay, and in this port we actually choose the starting address that we want. Okay, so let me just see if okay, everything's in school. And okay, now let's write our code. So I'll just copy and paste here. Actually, max transfer size, I think is already set. Cool. And basically, what we're going to do is that we and you know what? Let's change this to char. Okay, and let's also change here. Actually, let's copy this. So basically the idea is the user set a value, an address, and a size. Actually, let's say that if size is smaller than this guy here, maybe I'll change these numbers too big. Okay, and else okay, let's include our header. And let's just check if we forgot something. Actually forgot to define the depth. Okay, let's see. Actually, let's put this smaller, like I don't know, 200 kilobytes or something like this. Okay, well, let's run the synthesis just to verify if everything is okay. And yes, it seems okay. Here the utilization part, the instance, okay, and let's see if the interfaces are nice. So here we have an AXI light interface where we define the offset. Okay, actually by default this address here, it will start at 0. Okay, so the offset here, okay, this AXI light interface is going to actually append to this address. So normally the MIG start at like 800000 address, and actually put this address there, and then we are sure that that our IP core will write at the right memory address. Okay, so now let's create a test bench for testing all of this. Okay, let's see if we don't miss something. Yeah, seems that is working. At least at the C level, seems fine. Let me just put this just to make it more cool, like hexadecimal value. And well, if everything is fine, let's try also to co-simulate this. Let's synthesize again because he complained that something changed. Actually, yes, I changed this to a maximum memory of 256 megabytes. Okay, so let's ask to model sim dump trace all, because we want at some point to see the waveform, and let's see how it goes. Okay guys, it worked, but I did some changes while I was doing the pause. First, by some reason, and I really don't know why, if we set the parameter depth, okay, on the co-simulation just crash. Okay, actually if I generate again, okay, and run the co-simulation, at some point we're going to receive a message like the cosim.pc or something crash. It's going to come. Okay, so something like this. I don't know if maybe this is related to the size, like there is a maximum size. I would say that is strange. Anyway, let's try again. Maybe it's related to the size. And if you run cosine again, yes, seems that is something like size related, like actually touch here some limit, and that depth is simply is not acceptable. But well, so let's create again Actually, there is a new thing that probably I did not show to you guys before, is the usage of this volatile. Actually, it forces the synthesizer to always create a read and write in the memory. It's just to avoid that this is going to be cached somehow. Okay, so it actually is a good practice if actually you read and write multiple times in the same pointer in Vivado HLS. Okay, so let me generate again the IP core, because now I put that this value will come through the AXI light interface. Okay, so we have this guy here to select the offset, and this guy here which is actually going to set the start, stop, and set the value of the and the size of the transmission. Okay, what else we could be, just export this IP core, and we're going to use it in Vivado HLS. I'm actually going to create this, oh sorry, not in Vivado HLS, in Vivado I'm going to create a simple project in Microblaze that is going to use this IP core just to work as a main set. Okay, and will be cool. So let's create now the lab 8 project in the side of Vivado now. So lab 8 AXI master, for instance. Okay, as I said before, now we're going to use the Arctic 7 evaluation board because it has a zinc, and actually I want to play a little bit more with Microblaze. Sorry, it has a Microblaze, and well, so let's create the block design. Actually, it's really straightforward. We just first we add the MIG. Okay, we go to run connection automation just to put the port of reset. Don't forget that the sys clock by some reason is not defined in the constraint file, so you need to synthesize and manually set the right pin on the FPGA for this port. Okay, so now we add the Microblaze. Click on run block automation. Here, okay, just for a test, let's now use the UART feature that you can use with the through the debug module of Microblaze. Okay, now as you can see, the data cache and instruction cache is not connected now, and we're going to connect this with our MIG. Okay, probably Vivado, actually Vivado will put an interconnect in between. So well, oh sorry, the master will be cache. Okay, this guy and this guy here actually something's funny. So first let's connect this guy. Okay, so let's do a zoom here just to verify. So the instruction cache and the data cache are actually being connected to this interconnect here, and this interconnect is talking to our MIG. Okay, so here at the address editor you can verify that for the data we can actually access the MDM, which is the guy who is our debug module. Okay, but for instruction it's just the Microblaze local memory and the MIG. Now let's add as well the repository for our IP that we just created now in Vivado HLS. Okay, so we add repository. I really don't remember where we save it. So users Leonardo Labate. So so here. Okay, and we point to the solution. So cool. Set mem. Okay, which is this guy here. So now what we want, actually want the microblaze peripheral, where it is here. We want the microblaze peripheral channel to connect and control this AXI light, and our master bus we want to put on this interconnect here who talk to the MIG. Okay, so let's run the connection automation. Okay, so this guy and this guy we want to connect to the peripheral part. Okay, and here it is, and this guy here we want to connect to the MIG slave. So cool. So if we follow this guy here, is actually connected to this interconnect, which is talking to our MIG. If you go to the address editor again, you see, by the way, this offset address we need to set as the this is actually where this interconnect decided to put our MIG. Okay, so when we before, I don't know if you guys remember, actually let me change here to the screen, we set that we have an offset port, okay, which is going to where we're going to put these 8 billion thousand, I don't know. Okay, so let's synthesize, because we need to change the port. I always forget this. So source, create HDL wrapper, cool. Now let's okay guys, so now let's just set the IO. Okay, we have here the IO ports, and we want to see the device, what it is. Cool, here, oh sorry, package. Cool, I'm doing wrong. Okay, so the port that we want, the clock actually is CMOS LV CMOS 33, and the address of our clock in this case is N11. So here, so we just come here, N11, cool, done. Then we save. By the way guys, you could just create the constraint file, and then you don't need to synthesize just to have access to the package and to the pins and do all that. Actually it's faster. Everything will be like faster. We don't I mean, you just need to synthesize once. So let's generate bit stream. At this point I'm going to do a pause, and when it's done I will come back and we continue with our sample. Okay guys, now that the bit stream is done, there is just a little change that I did before I finish the video. I added a logic analyzer, okay, to verify what is going on in the output of our AXI master. Okay, but so let's just export the bitstream to Xilinx SDK. Okay, and I could launch SDK here, but I already have it open. So let's just analyze what the code does. Okay, okay. First here, as I said in the previous video, Here is a smaller version, oh sorry, version of printf. Okay, actually is the seal printf. Okay, it's I mean it's less big than a printf and sometimes nice. Okay, so one change, if we come here to configuration, is that now we are using the JTAG UART. Okay, and let's see. So the first thing that we did is we just initialize our AXI master object. Actually, this is generated through Vivado HLS. Here we define a size of an array. Okay, if we go back to the Vivado HLS, our max transfer size was set to 200. Okay, and here we just initialize the same thing as every other IP core. We just do lookup config, then initialize. Okay, so here we initialize these. We have this array who is actually going to point it to this address. Actually, this address is the beginning of the DDR. Okay, the DDR is placed here. Okay, this is the address of the MIG. If you go back here and go to address editor, you can see that look, the MIG is at this address. And here we did just a big offset just to guarantee that we are not going to write in our instruction code or data or something like this. Okay. If you really want to do some math, you can just go to the linker script and calculate your stack and heap size and the areas that you have on your code. But this is I mean, the probability that you are not going to touch your code are high. So what we do, we initialize the array to some known value, actually it's to 0. Then we set the address master to this address here, which is where we want to write. By the way, this matches with the address of our array. Okay, the size array in this case is 100. Okay, and some value. Then we just call start, and we wait while this operation is not done. Okay, as we seen before, this function actually return an integer. Okay, depending on the error, and then we just print the results. So let's just run this code here in GDB and see how it goes. So here we're just going to set the memory to some known value. So let's continue. Okay, if you go to memory, let's just show some X value. Okay, the memory has been initialized to 0. Okay, and here we're going to set the address. By the way, to this address here, set the size, and input some value. Okay, so let's continue. We step over, step over, step over, and if you do the start, the IP core will do its job and start to write you. Okay. By the way, let me put here unsign an integer. Maybe no. Okay, so actually we put 37 is actually 55 in X. So 55, 37. Okay. So actually you sing like this because we are writing byte a byte, and here is jumping in at every 4 bytes. Okay. So if we continue the program, now it's just going to print out the values. Okay, so let's continue. 55, 55, 55, and this will go up to 100. Okay, So guys, this is basically how the AXI stream works. Okay, let me just go back again to the code. We had our function setMem that you have an input value, an address, okay, and the size. We define this is the function just to have the start and is done information through the AXI light, but here is the important guy. Okay, we define the address master as a master AXI. We give a depth, okay, and remember that this depth can not be bigger than 200, otherwise it will crash. But basically this is kind of the max burst size that you can have in AXI master anyway. Okay, here we define that the offset will be set through AXI light as well. Actually, this is where we do this offset here. Okay, and the size and the value are through AXI light as well, and the code is quite simple. It's just a for loop, and we just put here an if you try to set more memory that the function can do. Okay, well, last thing that you could do is just go back to our guy. Let's just close the program here. Maybe if you guys are interested, we can see as well the result on our AILA core in our logic analyzer. But we're close to done. So what we do, for instance, when we have write valid in W ready to 1, actually just configure the logic analyzer to start to trigger at this point. Okay, so let's run our software again. Okay, so here is our data. Okay, okay guys, so hope you guys enjoyed, and anyway, I'm going to post this code and actually the other code in the end of this tutorial, in this set of tutorials, so you guys can later see how it works, and hope you guys enjoyed.